I'm going to tell you a little bit about my team. In short, where we are, how many people we are, what kind of work we do. Then I'm going to briefly define sublinear scaling. In short, it means maintaining more services with fewer people. I'm going to explain how we are doing in terms of sublinear scaling. Summary being, we're doing very well, mostly by having a very high degree of automation. I'm going to explain where we want to go in the future, which is maintaining even more services with even fewer people. And then I'll explain how we're getting there. And this is the point where we are starting to move beyond mere automation and making some changes to the way that we approach SRE. About the team. We are about 40 people in 2 different locations, one shard in London and the other shard on the US West Coast. And we are supporting about 400 services related to Google's advertising business. Google has a lot of SRE teams and a lot of SRE teams and ads, and among these we are one SRE team. These 400 services are not microservices. These are all fat binaries with lots of functionality, and they span several different user-visible products. So just from this number, you can probably tell that we are focused on doing operations work at a large scale. So we are not experts in the services that we support. As a matter of fact, if there's like some issue that requires me to look at source code, I'm probably lost, and I will immediately involve the developers of the service. So we do not really do deep dives into the services that we support. What we excel in is keep a large number of services healthy with only very few people. And this is reflected in our workload. Typically, about 30% of our time is spent on interrupt work. This is things like responding to pages, responding to tickets, and handling incidents. And about 20% is what we call service maintenance. These are kind of the non-urgent, ongoing things that you have to do to keep the service healthy, like capacity planning. And then 50% of our time, half of our time, is spent on project work. And this is things like designing our own logo. I would have really liked to show you that logo because it's awesome, but I was not allowed to. But I could get away with showing you this slightly censored version. But if you pay attention, we are allowed to wear the swag where the logo is on, so you may be able to catch a glimpse of it if you look around. No, seriously, project work, these are efforts that are aimed to reduce the amount of time that we spend on interrupt work on service maintenance. So these are things that affect all the services that we support. It's not increasing the reliability of one service, but reducing the work that we have with all the services. Our team is organized along several different axes. First of all, we have 2 on-call rotations that each cover about 50% of the services. Then we have several so-called service ownership groups. Each ownership group is responsible for roughly 2 to 20 services and is responsible for the ongoing maintenance of those services and typically has a little more insight into the services that are supported. And then finally, we have what we call projects groups. These are typically 1 to 5 people, and they're working on specific projects that fit into this definition of project work, meaning reduce the time that we need to spend on services. An example here could be we'd never want to do any manual work anymore when the data center goes down for maintenance. That would be a project that we would undertake. Let me move on to sublinear scaling. I think this is a very important concept because it really defines the difference between an SRE team and between an ops team. So what do I mean by it? Let's consider a typical business that has a number of services that it supports. And if the business is successful, then the number of services will grow over time. This is what I have plotted in the upper right. It's basically a linear increase in the number of services. And then you also need the number of people to keep those services working well and healthy. And in general, that number of people is some number n times the number of services. But now there's an important distinction. If you have a pure ops team, kind of the idealized case, then n is some constant. So you multiply the number of services with some other number, and you get the size of your ops team. This is what I've plotted in blue on the lower right. If you have an SRE team, however, then n should not be a constant, but n should itself be decreasing in time. This is what I have plotted in orange. So the number of SREs that is required to support the services should be growing more slowly than the number of services itself. This is what we call sublinear scaling. So it is not a statement about how much work is done, or it's not a statement about how the work is done, but it is a statement about what kind of work is done. At Google, sublinear scaling is a core objective for every SRE team. So an SRE is expected not just to keep the services healthy, but to reduce the amount of manual work that is necessary to keep the service healthy. And in my team, we have been relatively successful in that regard. I just said that we are currently responsible for about 400 services. This is up from 200 services about 3 years ago with the same team size. So we decreased N by a factor of 2. And we did this is primarily by having a very high degree of automation. So I'm going to tell you a little more about how our automation works. So before I tell you what we automate, let me explain how we automate, because the approach that we use may not be familiar to everyone. The classical way to do automation is what we call imperative automation. That's best illustrated with an example. Suppose you want to move a service from one data center to another, and you don't want to do it by hand, so you write something like a script that executes a number of predefined steps. This could be get quota in the new data center, start the process there, reconfigure your load balancer, then stop the process in the old data center and release quota there. And then you can just run the script and it'll carry out these steps for the service that you want to move. And this is great. It's much better than doing things by hand because you cannot forget a step and you can even do it for multiple services in parallel. But there's also a number of disadvantages. The first one is that this automation system needs a clean starting point. If your system is in some ill-defined state, for example, you reconfigure the load balancer, but the new job failed to start, then you cannot use your automation anymore. You first need to come in as a human and clean things up. You need to get in a well-defined state before you can use your automation. Corollary, you cannot use your automation to get out of some exceptional condition. The second one is that it is very difficult to handle failure. It is absolutely possible, but it is difficult. There's 2 cases to consider. The first one is the easier one, which is when one of your steps fails. You don't want to leave your system in an ill-defined state, so your automation script has to have some sort of rollback procedure to go back to whatever the status was before you started it. So this requires some extra code, probably already more than just necessary for executing the task. But there's something that's even harder to handle, and this is when the automation itself crashes. Now you're in an ill-defined state and your automation is not running. So what you need to do to handle this properly is constantly save state in some external system so that when the automation comes up again, you can recover the state and then, given the state, roll back to a clean state. Not impossible, but difficult. Another drawback is that you cannot change your mind once you have initiated a procedure. So assume you have some automation to scale up your service, and you just started it because you wanted to increase your replica count to 100. So while your automation is kind of churning to carry that out, you realize 100 is way too little. You actually need 200. And now you only have 2 options. The first one is wait for your script to complete and then start it again now with a new target. And the second one is abort the script, in which case, as we just discussed, it first has to roll back and then immediately go from like the current number of replicas to 200. But you cannot tell the script, actually, don't increase it to just 100, increase it to 200. You need to wait for it to complete, or you need to roll back. And the fourth drawback is you need kind of a separate recipe for every task that you want to automate. And there will be duplication of the steps. Very simple example, suppose you want to bring up a new service and you want to automate that. This will have the same steps 1 and 2, and it'll have a slightly different step number 3. So it'll look pretty similar to the move the service script. And then, if you need to add an additional step, like initialize a storage system or something, you have to remember exactly in which recipes you have to enter this additional step. And you may forget some. So while this is definitely a step forward from doing things by hand, if you have a lot of services and if you have lots of tasks to automate, then this is really not working well, but then it gets a little messy. So what do? We do something that is called declarative automation. And the central idea of declarative automation is that you tell the system the state that you want, but not the path to get there. Let's consider an example again. You want to move the service from one data center to the other. With declarative automation, this is not triggered by running a script, but you have a file, typically in a version control system, that defines your intent, meaning what should the system look like. And the intent file would say something like, service should run in data center bar, and then you change that to service should run in data center foo. And then you commit that change. And then a number of things start to happen. There's several components that we call actuators. These are constantly running services that try to bring your system in compliance with the intent. So there is a service that continuously tries to get quota in the data centers where your service should be running and release quota where it shouldn't be running. There's a second component that constantly tries to start and stop processes. Like it looks what processes are running, compares with the intent, and if they shouldn't be there, they are killed. And then there is a component that continuously reconfigures the load balancer so that traffic is sent only to the data centers where your service is supposed to be running. Now, I hope we all agree that this on its own would be a pretty terrible idea, because these components will step all on each other's feet. Like you would have quota being removed while there's a process running, or your load balancer would send traffic to a data center when there isn't a process running. Chaos. So you need something on top of it. And this is called a sequencer. The sequencer makes everything safe. And the way it does that is that every actuation component has to ask the sequencer for permission to proceed before it carries out a step. And the sequencer maintains a global list of invariants that must not be violated. What does that mean? Well, a simple example of such a rule is running a process requires quota. So if the quota actuator tries to release quota somewhere, but there is a process running, the sequencer would say, carrying out this step would violate one of my rules, so no. Or there is a rule that says sending traffic to a data center requires that there's a process running there. So if something tries to reconfigure the load balancer in a way that it sends traffic where there isn't a process running, that step would not be allowed. What this means is the way the automation works is if the status of your system differs from the intent, then it looks at all possible steps that you could theoretically carry out to get closer to the intent state, and then it carries out all the steps that are currently safe. This may not actually bring you to the final state, but after you've done like this first round of steps, you unlock a next round. Other steps are now suddenly safe. Like if you obtain quota, then suddenly the step to start the process there becomes permissible. This is a lot more complicated than writing a script, but it has several advantages. The first advantage is that you do not have to manage state, and you do not need to have a clean starting point. It doesn't matter what state your system is in, the automation will find a way from the current state to the intended state. Actually, your automation itself can crash at any point, and you can just restart it because it's stateless. It just looks at what's there, and it looks at where you want to be, and then it finds a path to this state. The other advantage is that we no longer have to deal with separate recipes for each task that we want to automate. The only thing that we have to maintain is this global list of invariants. You can also change your mind while the automation is running. Like, you can change the intent even if the system doesn't currently correspond to that intent. And the automation will automatically change course. So if you are currently here, you wanted to go here, then you're halfway there, and you can say, actually, let's take a different path now. So you can respond more quickly. Let me check. Oh yeah, and the final advantage is all changes to production automatically go through a version control system and are reviewed. They cannot be triggered by someone running a command somewhere. You can always look up when was it changed by whom. So that said, let me tell you what we actually automate. And the short answer is every change that can be expressed in the intent is automated, or the carrying out this change is automated. So let me start by describing what is actually part of this intent. The intent, a file in a version control system, defines for each service the redundancies that we want to have, meaning how many replicas do we want to be able to lose without the user noticing it. Then it defines the proximities that we want to have, meaning how close do we need to be to other dependent services. It specifies general dependencies, like these two services need to have the same version, or we need that and that much storage. It specifies the SLO and how we measure the SLO for that service. It specified a rollout policy. I'll go to that in a second. And it includes any service-specific configuration. This is typically in the form of command line flags. As I said, the automation can perform any step that is necessary to get the system into compliance with the intent. We already discussed one of these steps, which is moving the service to a different data center or starting it or stopping it. But as a matter of fact, this is rarely triggered by a change to the intent, because the intent doesn't say anything about data centers. Rather, what we have is kind of a second layer of automation that looks at the redundancy that we want to have, at the proximity that we want to have, at the traffic patterns that the service typically receives, and then makes a prediction for how many replicas we need and where on the globe should those replicas be, how much CPU does each replica need, and how much memory does each replica need. And this then, as kind of a second layer, triggers the actual moving of the service or the startup of the service. We also have automated monitoring and alerting. So the monitoring software is configured automatically to measure the SLO and to send us an alert if that SLO is threatened. So if there's a trend that looks like, okay, in 6 hours from now, we'll probably reach a threshold where we no longer meet SLO, then we get an alert ahead of time. We have automated load tests. That means every once in a while, the automation starts sending more and more traffic to one specific process until that process can no longer cope with the load. And then that information feeds back into this automatic selection of the deployment, meaning the data center, replica count, and so forth. We have lots of automation for releasing new versions. This starts with generating the binary, compiling it. It includes distributing the binary to wherever it should be running, and includes rolling out the change. Our configuration can be bound to specific versions of the binary. That means if we have to roll back, go back to a previous version, we cannot be in the situation where the old binary doesn't understand a newer configuration flag. As a matter of fact, rollbacks are just another change of the intent. So we can just change the intent to say this binary should have the previous version, and then the system will find a way to safely execute this rollback. It may actually decide to roll back other dependent services at the same time. And finally, we have policy enforcement. This basically means that you can add constraints that you cannot release a new version on a Friday afternoon, or you cannot make a change that affects production and canary setup at the same time. So all this automation has helped us a lot. As I said, we're maintaining twice as many services as before. And I've plotted this on the left, basically as a curve of effort per service over time. But recently, the gains that we get from the automation have leveled off. Progress is increasingly incremental. And what we found is that this is because other factors start to dominate. The time that we spend on service maintenance is no longer all that important. Instead, what we are limited by is the cost of onboarding services, the cost of handling pages on an ongoing manner, and the total cognitive load that we have from having to deal with so many different services. Cognitive load, in short, is the amount of knowledge that we absolutely have to have in our heads, that we cannot look up in order to work efficiently. So we said, if we want to scale up further than this, then we need to switch gears and take a different approach. Instead of looking for opportunity to shave off a few minutes here and there, let's take a step back and imagine that we are in the lower right corner. And we said this means that we are supporting not 400 services, but more than 1,000 services with the same team size successfully. And we asked ourselves, what would that mean? How would our day look like? So in a way, it's a different way to think about the problem space, and it was quite fruitful. Here's what we found. Our automation would look pretty much as it does now. Like, we have automated all the things that you can reasonably automate. However, there would be changes elsewhere. If we were in charge of that many services, then we have a lot more pages. Every service generates kind of a constant stream. So many of them would have to be handled automatically without ever involving a human on caller. We would spend very little time on onboarding. Actually, this would need to be something that the developers do. So we provide some sort of tooling or description that developers can use, and we take on the service once it is compliant with all our policies. Cognitive load would have to be very small per service. What this means in practice is that to us as the SRE team, all our services look exactly the same. They're all black boxes. We're not really sure what's going on in there. We just make sure that the black boxes run fine. So we would have almost no overlap in expertise with the developers anymore. And our value is suddenly somewhere else. We're no longer experts in the service. We are experts purely in running production systems and in providing a platform to run the services. So there's this saying that SRE means you no longer treat your servers as pets, but you treat them as cattle. And what we want to do is we apply the same thing to services. Our services are not pets. Our services are cattle. And most of the work that we do at the moment is focused on getting to this stage. And I'll give two examples. The first one is automatic and continuous production readiness reviews. In the past, we had a long checklist that we worked through and made sure that the service was compliant with every single bullet point. We have replaced this with a number of small programs, programmatic validators, that check if a service is compliant with a policy, and if not, then we get a bug. So the onboarding now means that we run all these validators against the service, and then we fix all the bugs, and then the service is compliant. This is already a big time saver, but what's much better is that we can now run these validators on an ongoing basis, so if there ever is a regression, we get notified, and this was not something that we had in the past. We're already using this in the SRE teams, and we're currently preparing that for use by developers. The main thing that is missing is more documentation. So the tool files bugs that tells, okay, this and this needs to be done, but in order for someone else to carry out the task, it's a lot nicer if you also describe why we have this particular requirement. And the second thing that I'm very excited about is automated incident handling. Like, if we get a page, there's a number of steps typically that are always the same. Check if there was a rollout that correlates with this, check if there's like config change. And if there's like a repeating pattern, of course you can automate it. So what we have just started is kind of a system that automatically annotates any incoming pages with additional information. So if the occurrence of a problem correlates with some other change, then that page gets augmented with the additional information. This helps with triaging, but it doesn't help us reduce the total load that we have from pages. So we have other efforts that are aimed at not involving the on-caller at all. The first one is to automatically redirect traffic if the problem is localized. Typical example, there's a canary binary and it has a problem, so all traffic that goes to this specific process encounters a problem. There's no reason, like every SRE would just say, okay, reconfigure the load balancer, send the traffic elsewhere. So why do we even do that by hand? No real reason, so that's why We are currently testing to automatically detect when this is the case, and then we don't ever get paged. The thing immediately gets turned into a bug. And then two other things that we are currently in planning stages is to automatically get what we call emergency quota. It just means if a service is short on resources, well, what do? We get a few more resources, and then we file a bug so that we can figure out what happened. Potentially can be automated as well. And we want to automatically escalate pages, meaning if we can tell right away there is a problem that needs to be fixed in the source code, because there's an exception being raised, then the page should automatically go not just to the SRE team, but also to the developer, because we don't have the expertise to fix the service. Like, we can mitigate things by using older versions, but we cannot fix it. So let me summarize. In my team, we doubled the number of supported services by increasing the degree of automation. But eventually, we got limited returns from that because we were limited by other factors. And we are in the middle of tackling these. First, by automatically handling some pages. Then by dropping production readiness reviews and automating them. And finally, conceptually, by shedding the service-specific knowledge that we have and becoming service-agnostic production experts. Thank you very much.